Why, hello. Today we're going to start Chapter 15, in particular Section 15.1, which deals with functions of several variables. Now, in our previous chapter, we dealt with what was called a vector-valued function. And we had a function like r of t that was equal to maybe like t squared, t cubed. And so what this function r did is it mapped something in the real numbers into something that was in three-dimensional space. Okay, and that was called a vector-valued function. Today, and in Chapter 15, what we're going to be dealing with is what's called functions of several variables. And in particular, if you look at this particular one right here, I have a function f of xy defined to be the square root of x plus y plus 2 all over x minus 3. And this is a function of two variables. Now, you don't have to have just a function of two variables. You can have a function of 3, 4, 5, as many as you need. So in this particular case, this function is a function of two variables, x and y. And quite simply, even if I didn't go over this, I think you guys would be able to figure it out on your own. If I wanted to evaluate f of 2 comma 3, you'd be plugging 2 in for x and 3 in for y. And you would get square root of, let's see, 2 going in for x, 3 going in for y, 2 going in for x. So let's see, 2 plus 3 is 5 and 2 is 7. So I have square root of 7 over a negative 1. Or minus root 7. Okay, that's all there is to it. Now, if you look at this function, if you notice what this function is doing, this particular function is taking a point in R2 space, and it's mapping it to a real number. So you're taking a two-dimensional vector or a two-dimensional point, and you're mapping it into a real vector. And this is called a function of several variables. If you look at this function, you'd say, well, for what values is this function defined? Well, if you look at the rule of that function, if I want to find out the domain, now notice the domain is going to be a subset of R2. If I wanted to figure out the domain of that function, I would look here and I'd say, I have two things going on. I have a square root of x plus y plus 2, and you can't take a square root of a negative, so I need x plus y plus 2 to be greater than or equal to 0. And in addition, the denominator cannot be 0. So I need x minus 3 not to equal 0. All right, and that would be my domain. My domain would be the set of all points x, y, such that x plus y plus 2 is greater than or equal to 0, and x minus 3 does not equal 0. Now, that's a very nice way to give me the domain, but to tell you the truth, it would be nice to be able to take this and figure out what the graph of what would the graph of all the points that are in the domain of this function look like. So here I have my graph paper, and I'm going to look here at my domain. And looking at my domain, I need to first of all sketch the region where x plus y plus 2 is greater than or equal to 0. And you've done that back in like your Algebra 2 days. If I want to graph the region x plus y plus 2 greater than or equal to 0, the border would be x plus y plus 2 equals 0. And if I solve for y here, the border of that region would be y equal to minus x minus 2. Okay, and that's a straight line. That's a straight line whose slope is negative 1 and whose y-intercept is negative 2. Okay, so if I want to draw the line y equals minus x minus 2, let's see, we just said the y-intercept is a negative 2. Okay, and the slope is negative 1, and I can write that as negative 1 over 1. So if my slope is negative 1 over 1, we can do change in y over change in x. So if I change y by negative 1, I change x by a positive 1. Change y by negative 1, x by positive 1, y by negative 1, x by positive 1. And the border is going to be this point. Now, since in my domain we could have x plus y plus 2 greater than or equal to 0, since we have the equal part, we're including the border. Okay, so I'm going to make that be a solid line. But we said the border was x plus y plus 2 equal to 0, but we want the whole region where x plus y plus 2 is greater than or equal to 0. So you probably remember from, I think we teach this in intermediate algebra here at Del Tech, to find out which side of the region am I going to shave. You can pick any point on one of the sides of the region. I'm going to pick the origin. If I pick the origin, if I plug in the origin into this inequality, x plus y plus 2 greater than or equal to 0, I get 0 plus 0 plus 2, 2 is greater than or equal to 0. So I say, yeah, that's a true statement. So since one point on the side of this line made this inequality true, all the points on this side. So I'm close to getting my region, except our domain said that the numerator had to make sense. That's what all the points x, y would make the numerator make sense. But we can't have x minus 3 equal to 0. So we said we had to throw out x minus 3 equal to 0. Or in other words, x could not equal 3. So since x can't equal 3, where I have x equal to 3, right here, I'm going to make this be a dotted line, put an open dot here. And so my domain is everything in this section, everything in this section, but don't include this line x equals 3 because that made the denominator equal to 0. So when I talk about this function, f of xy equals blah, 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 the only xy's that I can plug in to make this make sense, in which you'd get a real number, would be what I have shaded in. Okay, and many times when we deal with a function of several variables, it makes good sense to figure out what is my domain. You know, for what values is this function defined? Here's another multivariable function. G of xy equals y natural log of x squared minus y. If I want to figure out g of 2 comma 3, again, I'm going to plug 2 in for x, 3 in for y. So I'd get, putting a 3 in for y, 3 times the natural log of 2 goes in for x, so 2 squared is 4, minus 3, and that gives me 3 natural log of 1. Okay, and I hope you remember the natural log of 1 is 0, because e to the 0 is equal to 1. So this is 3 times 0, which is 0. And if you didn't remember that, you could have plugged it into your calculator and you would have said, yeah, I got 0. Now, what's my domain? Well, here, y can be anything, but the problem is, you probably remember with your natural logs, you can't take the natural log of 0 or a negative number. When you take a natural log, what's in here has to be positive. Because when you're taking the natural log of something, you're saying e to what power gives me this number? Well, e to any power is always positive. So in order for this thing to make sense, x squared minus y has to be strictly greater than 0. So if I wanted to write out my domain, it's the set of all ordered pairs x, y. That line, by the way, there means such that. Okay, so I'm giving the rule. I need x squared minus y to be strictly greater than 0. Now, writing that for my domain, that looks all well and good, but can I picture it? What does it look like? So let's go to our graph paper. We want to graph the region where x squared minus y is greater than 0. So putting that on the side here, I want to graph x squared minus y is greater than 0. That's what I want to graph. All right, so first of all, my border would be x squared minus y equals 0, or x squared equals y, or you might prefer to write it as y equals x squared. Well, everybody in Calculus 3, I think, can graph y equals x squared. If x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 4. If x is 3, y is 1, 2, 3, 4, 5, 6, 7, 8, 9 up here. And I have negative 1, 1, negative 2, 4, negative 3, 1. Now, since the original equation is strictly greater than 0, we're going to use a dotted line. So my border is going to be dotted. We're not including the border because the border would make x squared minus y equal to 0, and I would be taking the natural log of 0, which is undefined. And now we have to decide, are we shading in this part, or am I shading in this part? I don't really know. So what I'm going to do is I'll pick a point. This point right here, 1, 2, 3, 4. This point right here is 0, 4. X is 0, y is 4. So if I take the inequality x squared minus y greater than 0, if I put a 0 in for x, a 4 in for y, I ask myself, I'm checking the point 0, 4. Is that true? Is negative 4 greater than 0? No. No. So guess what? Since that point is not in the region, this whole section is not in the region, and we're going to shade everything on the other side of the region. And so my domain for this particular function is this part of the xy space. Okay, not hard stuff. All right, now this one, don't frantically copy it down, just read it. All right, it says, sometimes you can give your function as a rule. Another way, there's other ways that you can give values of functions, and one way is as a chart. So in this particular case, we say the temperature humidity index I, or humidex for short, is the perceived air temperature when the actual temperature is T and the relative humidity is H. So we can write your index is a function of your temperature and your humidity. Remember, in Delaware, everybody always says, you know, it's not the temperature, it's the humidity. You know, the more humid it is, the hotter you feel. Okay, so this is what this is making an attempt at. What does it really feel like the temperature is when you're outside? And it's a function of both how hot it is, but also what the humidity is. The following table of values of I is an excerpt from a table compiled by the National Oceanic and Atmospheric Administration. So, this is a chart, and what it's giving me is I is a function of temperature and humidity. So if I want to read this, if I say, let's say the temperature is 80 degrees and the humidity is 40%. It doesn't feel like it's 80 degrees. What does it feel like when it's 80 degrees? So I go across here for temperature, and I move over till I get to a humidity of 40. You with me? And I look down here and I say, when the humidity is only 40, it feels like it's 79 degrees outside. That's how you read the chart. Okay, not hard. So this is my T's, this is my H's, and to find out what my index is, I just look at the intersection of those two. So we have a few questions we want to answer. Okay. First one that we want to answer is, okay, good, that shows up pretty good. What is the value of f of 95, 70, and what is its meaning? Well, this is, remember, it goes temperature and then humidity. So if I go over a temperature of 95 and go to a humidity of 70, I come to 124. And what that means is when the temperature is 95 degrees and the humidity is 70 degrees, it feels like it's 124 degrees outside. Okay, let's look at another one. Let's look at this one. For what value of H is f of 90, H equal to 100? So I know the temperature is 90, so I crawl across here, temperature is 90, and it feels like it's 100. What's the humidity? It's 60%. Okay, not hard. All right, and let's do the last one. For what value of T is f of T, 50 equal to 88? So they're not telling me the temperature, they're telling me the humidity. The humidity is 50. It feels like it's 88, so what's the temperature? It's 85. So when the temperature is 85 and the humidity is 50, it feels like it's 88. Not hard. Everybody's like, yeah, Mrs. Strocko, get on with it. Now, there's another way that we can look at it. We can ask the following question. What are the meanings of the functions I equals f of 80, h and I equals f of 100, h? So let's look at the first one, f of 80, h. I look at I equals f of 80, h. Notice, for this particular case, the index is really only a function of the humidity. Do you all see that? Because we're told that the temperature is 80. So if I slide up here, when the temperature is 80 now, the temperature is given at 80, it's fixed at 80. What it's telling me is, you give me the humidity, and I will tell you what it feels like. So in this case, if the humidity is 40, it feels like 79. If the humidity is 60, it feels like it's 82. So what this is giving me, when they fix 80, the index is now just a function of the humidity. Okay, now on the flip side, they also wanted us to figure out, what does I equal to f of 100, h mean? Now in this case, they have fixed the temperature at 100. All right, and notice now I is again just a function of humidity. And now they're showing me when the temperature is stuck at 100, what does it feel like? Now if you notice, when the temperature was 80, do you notice when you increase the humidity, your perception of what it felt like just increased very, very slowly? You just went from 77 to 83. Or notice when the temperature was 100 and you increase the humidity from 20 to 70, look how much how much more quickly, how steeper the change was in what your perception is. Okay, so this is just giving you an idea of what multivariable functions can look like. Okay, moving right along. Let's look at these guys. Look at the function f of xy equals, notice I've thrown a lot of natural logs in because I think maybe we need to review. The natural log of x plus y minus 1. If I wanted to evaluate f of 1, 1, what we're doing here is we're just plugging in and we're getting the log of 1 plus 1 minus 1, which gives me the natural log of 1. And we just reviewed what was the natural log of 1? 0. If you don't remember that, you want to put that on a little cheat card and review it. The natural log of 1 is 0. Okay, let's try this one. We want to evaluate f of e comma 1. We're going to take the natural log of e goes in for x, 1 goes in for y, and we have the natural log of e. Remember, it's the natural log of e. It's 1. Because remember, e to the first gives me e. If you don't remember that, you want to put that on your little cheat sheet. And lastly, now, they're not asking for the domain, they're asking for the range of f. The range of f. That means this function is mapping things in R2 into R's. It's what kind of real numbers is this going to take on? Well, what kind of values does the natural log function take on? Everything. Remember what the natural log graph looks like when you look at the natural log graph? Remember y equals natural log x from last semester? The graph of y equals natural log x looks like something like this. It takes on all values from minus infinity to infinity. Well, for this particular function, I could let x be 1 and let y range over all the reals. And so I would be taking the log of all real numbers, and it would be taking on all values. So the range of this function is just all reals, which you could write like that, or you can write as minus infinity to infinity. Now, lastly, I ask, what's the domain of this function? Okay, what is the domain of this function? Well, remember, natural log, what can I do with natural logs? I can't take the natural log of 0. I can't take natural log of a negative. So what's inside the parentheses has to be greater than 0. Formally, you could write your domain as the set of all ordered pairs x, y such that x plus y minus 1 is strictly greater than 0. That's your domain. It's a subset of two-dimensional space. But I'd like to see what the graph of that domain of that function looks like. So we already did 2 of these, but I think we'll just do 1 more. We're going to get our border. Our border is going to be x plus y minus 1 equals 0. So that gives me y equals minus x plus 1. So I want to graph that line. So graphing that line, let's see. It has a y-intercept of 1, and it has a slope of negative 1. So I'm going to go down 1 over 1, down 1 over 1. Looks like this. But now, for the original function, we were graphing it for strictly greater. So when it's strictly greater, do we include the border? Absolutely not. So we just make it a dotted line. But now we have to decide which side do we shade in. So we got to pick a point. I think I'll pick, we need x plus y minus 1 greater than 0. Why don't we pick this point right here? This point is 2, 3. Okay, now we're checking the inequality x plus y minus 1 strictly greater than 0. So 2 goes in for x, 3 goes in for y. We're checking the point 2, 3. And so we get 5 minus 1 is 4. Is that greater than 0? Yes. And so since it's a yes, since 2, 3 works, everything on the side of 2, 3 works. And that's what my domain was going to look like. This function, natural log of x plus y minus 1, is only defined for these values. If you pick any point on this side, you'll get the log of a negative, and the function's undefined. Okay. Sketch the domain of this function. F of xy equals 1 plus x minus y squared. What is the range of f? Well, first we want to do the domain. Okay, we want to do the domain. So my domain, it's going to be the set of all x, y, such that 1 plus x minus y squared is greater than or equal to 0. That's what formally your domain is going to look like. Because we only can take the square root of 0 or positives. Now, to figure out what the sketch of that domain looks like, I need to have 1 plus x minus y squared equals 0 is going to be my border. All right, or we could write this as x is equal to y squared minus 1. Okay, what's the graph of that going to look like? What's the graph of that going to look like? What does x equals y squared look like? X equals y squared, yeah, it looks like a sideways parabola, right? So x equals y squared, we all should know, looks something like this. But if I subtract 1 to it, what am I going to be doing? I'm going to be moving it to the left one. So it's just going to look like that somewhat. Okay? So if I want to make a chart, I want to graph 1 plus x minus y squared equals 0. I'm claiming when x is a negative 1, when x is a negative 1, let's write this as 1. Let's write it as x equals y squared minus 1. So when y is 0, you can see x is a negative 1. When y is 1, x is 0. When y is 1, x is 0. Or when y is a negative 1, x is 0. I mean, when y is 0, when y is 0, x is a negative 1. Let's just make a little chart here. So we're letting y be 0, plus or minus 1, plus or minus 2, plus or minus 3. You pop in a 0 here, you're going to get 0 minus 1 is a negative 1. Plug in a 1 here, 1 squared minus 0 is 0. Plug in a 2, 2 squared is 4, minus 1 is 3. Plug in a plus or minus 3, 9 minus 1 is 8. So we're going to have x is 0, x is 0, y is plus or minus 1. X is 3, 1, 2, 3. Y is plus or minus 2. And x is 8, 1, 2, 3, 4, 5, 6, 7, 8. Y is plus or minus 3. And the original domain was greater than or equal to 0, so it's going to be a solid dot. Okay? And we need, for this particular function, we need x plus y minus y squared to be greater than or equal to 0. So I'm going to check the origin and see if it works. And if you plug in the origin, 0 for x, 0 for y, what do we get here? We get, just checking the point 0, 0. I get 1 plus 0 minus 0 is greater than or equal to 0. That's a yes. And so this is what the domain looks like. It's everything inside there. Okay? That's what its domain is. The range? Well, what do you think the range is? What values does this function take on? When you plug in all the numbers in this region, what values are you going to get? Well, gee, if you let y be 0, or you let y be plus or minus 1, if I just let y be plus or minus 1, or just let y be 1, notice you get f of x comma 1 equals the square root of 1 plus x minus 1. You're getting the square root of x. Well, for different values of x, you're going to go from 0 to infinity, right? And whenever you take a square root, you can't get a negative. So the range is going to be all numbers from 0 to infinity. This is not hard stuff. This is pretty easy stuff. This one, let's just do the domain. Square root of x plus square root of y. For what values is that function defined? You can't take the square root of a negative here. You can't take the square root of a negative here. So this domain would be the set of all x, y, such that x is greater than or equal to 0, and y is greater than or equal to 0. Well, what does that look like? Where are all x's positive or 0 and y's positive or 0? You could have here, here, and it's the first quadrant. That function's only defined on the first quadrant because you can't take the square root of a negative, so x can't be negative, neither can y. Okay, let's look at another one. Find and sketch the domain of this function. Okay, now looking at this function, what can't you do with a rational function? What can't you do? What's your no-no? You can't have the denominator equal to 0. So x plus 3y cannot equal 0. So if I want to write my domain out formally, it would be the set of all x, y, such that x plus 3y does not equal 0. Well, what does x plus 3y equal 0 look like? What does that look like? I think it's a straight line, isn't it? If I solve for y, I get 3y equals minus x, or y equals minus 1/3 x. That's in the form of y equals mx plus b. It's a line whose slope is minus 1/3 and whose y-intercept is 0. So let's see, we said y-intercept is 0, slope is minus a third, down 1 over 3, down 1 over 3, down 1 over 3. Or we could go up 1, back 3, up 1, back 3. Now, since we can't have x plus 3y equal to 0, this guy's thrown out. I'll make him be a dotted line. So that line is thrown out, but everything on this side, everything on that side is okay. Okay? Because everything on that line makes x plus 3y equal to 0, which is a no-no. Okay, so this domain is like two half-planes, and not including their edge. Find and sketch the domain of this function. Okay, now things are getting a little bit more clever here. We have f of xy equals square root of y minus x times the natural log of y plus x. So I'm thinking there's two things going on here. Square root of y minus x has to make sense, and natural log of y plus x has to make sense. For this one to make sense, what do we need? We need y minus x to be greater than or equal to 0. So we need y to be greater than or equal to x. But at the same time, we need this to make sense, because you have to have this make sense and that make sense to multiply them together. So we need y plus x to be what? You can't take the log of 0 or a negative. Strictly greater than 0, right? So we also need y to be greater than minus x. So since we need this and this, our domain is going to be the intersection of those two sets. So to sketch it, let's see, that's showing up. That's not showing up too good. We can just fold this down and that'll be better. To sketch it, first of all, I need this. Well, y equals x is the straight line, y equals x. And since it's greater than or equal to, we're going to make it be solid. I'm just picking the points on the edge, y equals x. And it's going to be a solid line. Y greater than or equal to x is going which way? Up. Because we're making y greater. If you notice, if you take the point 0, 3, you can see it makes sense. So what I've shaded right now is just what makes this true. Now, what if I want to graph y greater than negative x? Well, the border is y equals negative x, and I know what that looks like. It's this line right here. Y equals negative x looks like this. But this region is y greater than negative x. This was the line y equals negative x. And if we want to go greater, which way are we going to go? Above. So we have to make this make sense and this make sense. Our domain is the intersection of those two. So it is not including this edge, including this edge, and we're shading this region in here. And everything in here is the domain. Just that wedge of two-dimensional spaces in my domain. Okay. Moving right along. Okay, now we've done plenty of finding the domains. Now let's go and talk about well, I have one more here. Maybe I should do it. Let's do it real quick. This one's sort of fun. We have x squared plus y squared minus 1 plus the natural log of 4 minus x squared minus y squared. And the reason I think that's sort of fun is this has to make sense. Square root of x squared plus y squared minus 1 has to make sense. And in addition, the natural log of 4 minus x squared minus y squared must make sense. So putting it down the middle, for this to make sense, what's underneath the square root has to be greater than or equal to 0. So x squared plus y squared has to be greater than or equal to 1. Your border would be x squared plus y squared equals 1. What does that look like? A circle of radius 1 centered at the origin, right? So if I put that here, I wanted to graph that. A circle of center 0, radius 1, I can go up 1, down 1, to the right 1, to the left 1. And since we have x squared plus y squared greater than or equal to 0, my border is solid. Okay? Now, which way are we going to go? Are we doing inside the circle or outside the circle for x squared plus y squared greater than or equal to 1? Outside. Okay? So we're going to go the outside of the circle. And if you think about it, take the point 2, 0. If you plug it in here, 2 squared plus 0 is definitely greater than 1. All right, but we also have to have this baby cakes to make sense. We need to have, in addition, the log of 4 minus x squared minus y squared to make sense. We can't take the log of zeros or negatives, so we need 4 minus x squared minus y squared to be greater than 0. So I need 4 to be greater than x squared plus y squared. So my border is going to be x squared plus y squared equals 4. What's that a graph of? A circle. Center 0, 0. What's the radius? 2. And when I do my circle, am I going to make it a dotted line or a solid line? Since it's strictly greater, it's going to be dotted. Circle of radius 2, 2, 2, 2, 2, but I have to make it dotted. Okay, pretty sad looking circle, but you can use your imagination. And for this guy, we need to have x squared plus y squared to be less than 4. I just rewrote this. X squared plus y squared is less than 4. So if this is the border, and you need x squared plus y squared to be less than 4, which way are we going to go? Inside. So for the first piece to make sense, we have to go outside the red circle. And for the second piece to make sense, we have to go inside the blue circle. And so the intersection of those two is this donut. And our domain includes the red circle, but does not include the blue circle. Isn't that cool? I think that's cool. Okay, now, it's nice to be, every time you have a multivariable function, many times it does help if you think about for what values is this function defined. Also, it's nice to graph the function. Now, how do we graph these functions? Well, we're going to, when we have a function of 2 variables, we will always think of f of xy as being z. Z is equal to my f of xy. So when you make a graph of this function, you're going to graph the points whose coordinates are xy, which are the ones that you're doing that, and you're going to do that in your xy plane. And then your height that you go up, z, will be your f of xy. Okay, you with me? So for some of us, it probably would be helpful if I wanted to graph f of xy equal to y, I just say, okay, since f of xy is my z, I want to graph z equals y. What's that going to be a graph of? It's going to be a plane. Now to draw my plane, remember when you have a function, okay, for a 3-dimensional surface in space, and it doesn't have one of the variables. In this case, we don't have the variable x. What we're going to do is we're going to draw z equals y just in the zy plane. Remember? And then we're going to drag it parallel to the x-axis. Well, what does z equals y look like in the zy plane? It really goes straight this way, but I'm going to just draw it up at a little bit of an angle to make it easier for me to draw. But this is the line, z equals y. I made it off by a little bit because I don't want it to be exactly like him. I need him off just a little bit to help me with my picture. Okay? And what I like to do, if I'm going to drag him along, I like to extend the x-axis and draw a zy plane here. And then I want to take this little red line and I want to draw him parallel right here to help me. And then we're pulling him along the x-axis. And as you can see, what you're doing is you're getting this plane here. You're getting a plane that's at 45-degree angle with the xz plane. So what do we have here? We definitely have a plane. Okay, want to do another one? Let's do another one. Suppose we want to draw f of xy equals 4 minus 2x minus y. What I do is I just remember z is equal to f of xy. So wherever I see f of xy, I put z. Does anybody recognize that? You might feel better if you put the x's and the y's to one side. What's that a graph of? A plane. Remember, anything in the form of a times x plus b times y plus c times z equals some number is always a plane. That's a plane for sure. How do we draw that plane? The easiest way is to get your three intercepts, your x-intercept, your y-intercept, and your z-intercept. So if I let y and z be 0, what's x? 2x equals 4, x is 2. If I let x be 0 and z be 0, what's y? 4. And if I let x be 0 and y be 0, what's z? 4. So now I have 3 points. I've got 2, 0, 0. I've got 0, 4, 0. And I got 0, 0, 4. And then you connect the dots. And that gives you a good idea of what the plane looks like. Of course, the plane goes on forever, and I've just drawn a triangle. But think of it as taking this is your little wedge that you're going to glue your laminate on. That's your plane that goes forever. All right, now of course we know we got to look at our paraboloids and hyperboloids and all that type of stuff. So what if I have this? This is z equals x squared plus y squared plus 1. What's that going to look like? Now, you probably remember from from chapter 13, when we had z equals x squared plus y squared, that was a paraboloid, right? It looked like this. Okay? Now if I have z equals x squared plus y squared plus 1, what am I doing to all my y coordinates? All my z coordinates. What am I doing to all my z coordinates? I'm raising them 1. And if I increase all my z coordinates by 1, what's happening to this graph? We're going to take this paraboloid and we're just going to lift it 1 unit. So instead of hitting the origin, he's going to hit z equals 1. And he will look like this. And this is a nice thing to remember. If you have a function like z equals f of xy, and you know what its graph is, in this case, f of xy I'll call x squared plus y squared. If they give you xy plus 1 or plus 2 or plus 3, what that's doing is it's going to raise you 1 unit. And that's exactly what we did here. We're raising that paraboloid just up 1 unit. Okay, let's do another one. Ooh. This one I look at it and I have no clue. Do you? Sketch the graph of f of xy equals 4x squared plus y squared. So what I'm going to do, I'm going to say z equals square root of 4x squared plus 9y squared. Okay, and let's square both sides. That would give me z squared equals 4x squared plus 9y squared. And if I wanted to get 0 on this side, that would give me 0 equals 4x squared plus 9y squared minus z squared. When you had 0 on the one side and you have x squareds and y squareds and z squareds, what was that a graph of? When it was a 0, what was it a graph of? Cone. Who's the odd guy out? Z is the odd guy out. So along what axis is my cone? The z. Now normally my cone is going to look like this. Okay? That's what my cone looks like. But let's go back to the original equation. The original equation is z equals square root of 4x squared plus 9y squared. So what can you tell me about z? Z is always positive. So I take out my eraser and say, oh, z can't be negative, so I can't be below the xy plane. And so this graph is just going to look like that. Okay? Let's do another one. This one, z equals square root of 36 minus x squared plus y squared. What do you think you're going to do to get a handle on this? I think you're going to square both sides, don't you? Let's square both sides. If I square both sides, I get z squared. But just remember, since z equals square root, z is positive. All right, so I get square root of, and when you square a square root, you get this. To get a handle on it, let's put the x squareds and the y squared. So I'm going to add an x squared to this side, subtract a y squared. When you have x squared, y squared, z squared, and anything but 0 on the right-hand side, you have a hyperboloid How many minus signs do I have? So it's a hyperboloid of? Aha! It's going to be a hyperboloid of one sheet. And the reason it's one sheet is because I have one minus sign. And since the one minus sign goes with the y squared, it's going to be along the y-axis. I don't care about things being drawn real exactly, but I'm just going to extend my y-axis here. My hyperboloid is going to look like this. Now, normally your hyperboloid went all the way down here with little circles around here, except we're only getting the top half of the hyperboloid. You with me? Because we're only getting it for the part where z is positive. So instead of it going all the way around, this is going to go down till I hit the xy plane. You with me? And you'll have another piece like this. And then it'll look like that. You with me? Because you're only having the top half of the hyperboloid. You're going to, you know, that tube, you're cutting it in half. You're just getting the top half. Okay. All right. Level curves. Level curves. What are level curves? Level curves are something that are going to be very important in the next couple lectures. All right. What is a level curve? Notice when you have a function f of xy, z equals f of xy. You're taking points in the xy plane, right? And you're doing something with them to get a real number, to get your z. So your domain is always something in the xy plane. Okay, it's part of the xy plane. All right, but now you look at your function and you say, what points xy make f of xy equal to some constant? And if you just draw those points that make f of xy equal to some particular number, that's called a level curve. So like in my domain, maybe I have all these points connected. This is called a level curve if everything along this curve has f of xy equal to maybe some number. Maybe it's 5, which means f of xy is 5 for every point on this. Now, why do they call them level curves? Well, for all of those points, when you plot z, z is going to be 5. So they're all level. You're with me? They're all level. If you graphed all those points in the actual function, they all those points that correspond to those points in the domain all have the same height. And that's why they're called level curves. But the bottom line is, you have level curves with equations f of xy equal to some constant. All right, so now let's do some of these. Sketch the level curves of the function f of xy equals 8 minus 2x minus 4y for the values k equals minus 8, 0, 4, and 12. All right, so we're first going to do it for k equals negative 8. So we need we want to know what points have f of xy equal to a negative 8. Now what's f of xy? F of xy is 8 minus 2x minus 4y, and we need that to equal a minus 8. Notice your domain are points in two-dimensional space. Okay? Well, what does this graph look like in two-dimensional space? Well, let's see. I'm going to add a positive 8 to both sides and get a 16. I'm going to add 2x and I'm going to add 4y. If I divide through by 2, what's that a graph of, people? What's that a graph of? What does x plus 2y equals 8 look like? It looks like a straight line. If I want to draw that straight line, let's see. When x is 0, 2 points real quick. How about 8, 0? 1, 2, 3, 4, 5, 6, 7, 8. And how about 0, 4? 0, 4. And it looks to me like if I go down 1 over 2, down 1 over 2, down 1 over 2, there's my line. Up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2. This line, all of these points on this line have f of xy equal to negative 8. Every single point on that line, if I evaluate it using this function, what am I going to get? I'm going to get a negative 8. Now I want to know where are all the points that make f of xy equal to 0. I want to get the level curve for f of xy equal to 0. So I take the function 8 minus 2x minus 4y, set it equal to 0, and let's see, that would give me 8 equals 2x plus 4y. If I divide by 2, 4 equals x plus 2y. What does that graph look like? A straight line. And let's see, give me 2 points on the line. If I let x be 4 and y be 0, that works. Or if I let x be 0, y is 2. Give me 2 points, I can draw my line. So if I draw this line, let's see, we have 4, 0, 1, 2, 3, 4, and 0, 2. This looks like he's going down 2 over 1, down 2 over 1, down 2 over 1. It'd be nice if I had brought a ruler, but I didn't. This level curve looks like this. And what do I know about all those points? Every single point on there, if you evaluate it on that function, you get f of xy to be 0. You with me? I don't know if I want to do it for 4 and 12, but let's do it at least for 4. Doing it for 4, if I want to get the level curve for f of xy equal to 4, again, I take my f of xy, set it equal to 4. I guess I could subtract 4 here, add these guys. How about divide by 2, just to graph the line a little bit easier. Points that are on that line would be x could be 2, y 0, and another one, how about x is 0, y is 1. Okay, so plopping that on here, I need the point 2, 0. Let's do it in green. 2, 0, and 0, 1. Going down 1 over 2, down 1 over 2, down 1 over 2, down 1 over 2. Do you notice level curves don't intersect? And this line represents all the points xy for which f of xy was equal to 4. For this particular guy, what do you think all your level curves are going to look like? They're going to look like straight lines. Okay? And the thing I want you to notice is, if you had a little guy walking along a level curve, and he has a little readout, and on his readout, it tells us what the value of the function is, f of xy at that point. If he's moving along the curve here, his readout's going to be continually -8, -8, -8, -8, -8, -8, with his little Geiger counter. Where if you have another little guy walking along here, and he looks at what's f of xy as I walk along that curve, it's going to be 0, 0, 0, 0, 0. But if he goes off that line, f of xy is going to change. Pretty easy, isn't it? All right, so it's important, it's very important for us to be able to draw level curves for a function f of xy. So let's do a couple of these and just talk about what they would look like. All right? Sketch the level curves. Now notice I didn't give myself graph paper because I don't want to be so exact this time. What if I want to sketch the level curves for the function g of xy equals square root of 16 minus x squared minus y squared? Please notice, people, level curves are drawn in the domain of the function. This function's mapping points in R2 into numbers. Your domain is two-dimensional space. Your domain is the xy plane is what it is. So your level curves are always drawn in the domain. You with me? So I say, okay, if I want g of xy to equal, they want k equals 0, I need square root of 16 minus x squared minus y squared to be 0. Square both sides, Mrs. Strocko, I get this. Drop kick the x squared and the y squared to one side. What am I getting? A circle. A circle of radius. A circle of radius 4, centered at the origin. Okay, let's just do a couple more. What if I want to get the level curve g of xy equal to 1? In this case, you'd have square root of 16 minus x squared minus y squared equals 1. Square both sides. I could subtract the 1, add the x squared plus y squared. I'm going to get a circle again, a circle of radius root 15. Somebody on the calculator, do root 15 for me and tell me what it is. 3 point something. 3 point what? 8.7? Okay, we're going to round it off to 3.9. You get the idea. Let's get the level curve for k equal to 2. That would be g of xy equals 2. So g is 6 minus x squared minus y squared equals 2. Square both sides is 16 minus x squared minus y squared equals 4. So I get 12 equals x squared plus y squared. That's again a circle of radius root 12. And somebody do me the square root of 12 for me. And round it off to tenths. That's going to be 3.5. I think we did enough. We're not going to do the third one because I'm getting bored with it. All right? So what do we have here? Let's draw our level curves. The level curves are, for the function g of xy equals square root of 16 minus x squared minus y squared, the domain of this function is R2. It's the xy plane. The first level curve for g of xy equal to 0 turned out to be a circle whose radius was 4. 1, 2, 3, 4. Centered at 1, 2, 3, 4. 1, 2, 3, 4. Here's my circle. Sad circle, but you can use your imagination. And that is g of xy was equal to 0. You have a little guy walking along that track. G of xy is always 0. The second one, when I wanted to do g of xy equal to 1, I ended up with the circle x squared plus y squared equals 15. That circle had radius 3.9. Well, gee, a radius of 3.9 is just a little bit shy, but it's still a circle. You have a little guy walking along, the blue guy, g of xy, was always equal to, 1. And thirdly, we want to find the level curve for g of xy equal to 2. Anybody walking along g of xy equals 2 is walking around a circle of radius 3.5. 3.5, 3.5, 3.5, 3.5. Another circle. What does it look like all your level curves are going to end up being? G of xy equals 2. And the whole thing is, if you're moving along a level curve, if you're walking on that curve and not deviating, and you're looking at what g of xy is as you're walking along, g of xy is always 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. If you're walking along the level curve, g is not changing. So if you look at your graph of the function above your head, it's going to be level above your head as long as you stay on your level curve. Sketch some level curves of this function. Let's talk about it. What if I want L of xy to equal some constant k? And I get 2x squared plus y squared equal to some constant k. Let's let k be 1. Or why don't we try k to be 2, or k to be 3. What's the graph of this going to look like? What's x squared plus y squared equals a positive number look like? What is it? It's an ellipse. It'd be a circle if it was x squared plus y squared, but since it's the one guy gets weighted, these are going to look like ellipses. Now, I'm not going to draw all these ellipses, but if you drew 2x squared plus y squared equals 1, y is plus or minus 1, x is whatever square root of a half is, square root of a half is, I think, 0.7. So it's going to be about 0.7. So it's a little bit flattened ellipse. Nope, so you had to come all the way down here to 1, up to 1, and down. And you got an ellipse. And this ellipse, he's going to be, you divide by 2, you're going to get x squared plus y squared over 2 is equal to 1. This ellipse is crossing x at plus or minus 1. And there will be like concentric ellipses. Okay? So you're going to have ellipses that go like this, bigger, 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 and you're going to have ellipses smaller, smaller, smaller. Okay? So the big thing to realize is when you got x squared plus y squared equals a number, you've got yourself an ellipse. Okay? We all doing okay? All right. Draw a, now you're saying, Ms. Strocko, you didn't use this word yet. Draw a contour map of the function f of xy equals x squared minus y squared for several level curves. All a contour map is a drawing of a lot of the level curves. As many to make it interesting. Okay? So let's do a couple and let's see what we can get here. Notice, what if I want f of xy to be 0? Let's do that level curve first. I'd have x squared minus y squared is 0. This one gives students a lot of trouble. What does the graph of x squared equal y squared look like? It's two straight lines. Take the square root of both sides, you'd have y equals plus or minus x. It's two straight lines. Because if you take the square root of both sides, you know y could be equal to x or y could be the opposite of x. So my first level curve is going to be y equals x and y equals minus x. And this is the level curve f of xy equal to 0. Okay. Now, I think most of you would agree, your f of xy, your level curves could be equals a positive constant or a negative constant. So what if I take f of xy equal to like 1? I get x squared minus y squared equals 1. What's that a graph of? What's that a graph of? If it was x squared plus y squared equals 1, you've got a circle. If you weighted like the 2 or the number in front of the x squared or the y squared and had like 2x squared plus 3y squared, it was an ellipse. But when you got a minus sign, what do you have there? Hyperbola. And where is the hyperbola crossing what axis? When x is first, it's crossing the x-axis. Notice, if you let y be 0, you get x to be plus or minus 1. You see that? So if I want a hyperbola that's crossing the x-axis at plus or minus 1, it's going to look something like this. And this is f of xy equal to 1. Now, what if instead, and I'm getting tired of writing, what if I make f of xy equal to 2? This is still going to cross the x-axis, but if you let y be 0, what's x? X squared is 2, so x is plus or minus square root of 2. You with me? You see, because I'm finding the level curve for f of xy equal to 2. And notice with this equation, if you let y be 0, you get x squared is 2, or x is plus or minus root 2. Well, root 2 is about what, 1.4? 0.1.4? So your hyperbola is going to look something like a little bit further over. Well, you get the picture. What's going to happen? You're going to have a hyperbola out here. You with me? Another one out here, right? I wonder, do I get any up here? No? Okay, let's look. So far, I've only done level curves for zeros and positives. What if I want to get a level curve for f of xy equals a negative 1? I get x squared minus y squared equals a negative 1, which, if you multiply through by a negative, this hyperbola is y squared minus x squared equals, oh, wait a minute, I multiplied through by a negative, so I got y squared minus x squared equals 1. This hyperbola is crossing what axis? The y-axis. And when x is 0, where is it crossing the y-axis? At plus or minus 1. So the level curve for negative 1 goes like that. And that's f of xy equals negative 1. F of xy equals negative 1. And if we did it for negative 2, you'd get another one. And then if negative 3, you'd get a negative 1. And isn't that cool? Isn't that cool? And for each of these, this is called a contour map. If any of you, or I don't think I have in the TV studio any geography majors, but if I have any geography majors, the beauty of this is, like if your function f of xy was the altitude on the map, if you mark along a level curve, all those points on the map have the same altitude, same height, z. All right, so we did one for that. Let's do one more. What if I wanted to draw a contour? This one's easier. I probably should have done this one first. What if I wanted to draw a contour map of f of xy equals y minus x squared, showing several level curves? This one's a little bit easier. Let's do f of xy equal to 0. That would give you y minus x squared equals 0, or y equals x squared. What is that, people? That's a parabola, right? Is it okay if I draw y equals x squared without your help? 2, 4, 2, that's not a 4, 2, 4, and 3, 9, 1, 2, 4, negative 3, 9. This is the level curve for f of xy equal to 0. Now what if I want to find out the level curve for f of xy equal to 1? Then I need y minus x squared to be 1, or y equal to x squared plus 1. People, what does y equal x squared plus 1 look like? It looks just like y equals x squared, right? But it gets moved up one. Do you mind if I don't be too fancy? Just move them up one. And if I made it be equal 2, you'd have a 2 here, and you move them up 2, right? And what if I wanted to make f of xy equals a negative 1? Then I'd have y minus x squared equals a negative 1, or y equals x squared minus 1. I'm going to move the parabola down. And as you can see, your level curves never intersect. They never intersect. And again, if I had a little guy walking along here, f of xy is always equal to, for that guy, f of xy is continually equal to a negative 1. Because those are all the points for which f of xy equals that one value. Notice, this function mapped something in two-dimensional space into the reals. When we talk about level curves, we're drawing curves in the domain. The domain is R2, two-dimensional space. Now what if I have a different kind of function? This function, f of xyz, is equal to x squared plus 2y squared plus 3z squared. Notice this function is defining something in three-dimensional space to the reals. So if I wanted to draw level curves, they would be where? In R3. You with me? Because this function's defining its domain is in R3 because it's taking a point in three-dimensional space and doing something to it to get a real number. Now why am I calling them surfaces for the three when you have a function of three-dimensional variables? Notice this. What if I wanted to look at f of x, y, z equal to 0? I get x squared plus 2y squared plus 3z squared equals 0. What point satisfies that equation? Last time I looked, x squared's positive, y squared's positive, z squared's positive. Positive plus a positive is plus a positive is a positive. Is there any point that's going to work?
0.
The origin. The origin works. So the level curve for this equation is just the origin. Because if you take 0 squared plus 0 squared plus 0 squared, you definitely will get. So my first level curve is just a stinking point. Okay. Now, let's try f of x, y, z equals 6. What's that a graph of? X squared plus y squared plus z squared equals 6. When you got all squares and all pluses and you got a positive number on the right-hand side, what do you got? An ellipsoid. And notice, did it matter that I had 6? I could have had 12, I could have had 24, I could have any. You're going to have ellipsoids. And so the reason we call them level surfaces is that in 3D, you're not getting just little curves, you're getting surfaces. For this particular one, I chose this one because the numbers are easy. How do you draw this ellipsoid? Do your intercepts, right? Your intercepts. If I let y and z be 0, x is plus or minus square root of 6. Somebody want to do plus or minus square root of 6 for me on the calculator? So I can't see mine. What is it?
2.45.
What is it? 2.45. We'll round it off to 2.5. If I let y and x be 0, I get 3z squared is 6, so z squared is 2, so it's root 2, which is 1.4. I can do that one in my head. And if I let x be 0 and z be 0, I get 2y squared is 6, so y squared is root 3, and that's about 1.7. So if I wanted to draw that, 2.5, I'm not real good with ellipsoids. Same amount back. 1.4, how about here? 1.4 and 1.7, oh, that was 1.7. And for the z's, how about 1.4, which would take me about here. 1.4 right here. So if I connect the dots for the y's, for the x and the y's, I get this. If I connect the z's and the x's, whoops, x, I should have gone to here. Not too good, guys. And this one's going to be coming down around like that. Not the best picture, but as you can see, it's an ellipsoid. And as you change your f of x, y, z equal to some other constant, you're going to get x squared plus 2y squared plus 3z squared equals some other constant. And they're just going to be bigger ellipsoids and smaller ellipsoids. And do the ellipsoids ever intersect? No. Because if you have a point that's on two level curves, its function value equals two different values, which it can't happen. Okay, one more. This one I should have done first. What would be the level surfaces of this guy look like? F of x, y, z equal to, let's say, some constant. That gives me 10 minus x minus 2y minus 5z equals k. What's that a graph of? Should we pick different k's? Why don't we let k be 0? Then that gives me 10 equals x plus 2y plus 5z. What's that a graph of? A plane. Right, it's going to be a plane. X is 10, y is 5, z is 2. And then what's going to happen is you're going to have parallel planes. You with me? You're going to have different parallel planes as you let k be different values. Okay? So your level surfaces, now notice if you move along this one plane, every f of x, y, z on that plane would be equal to 0. Okay, now lastly, I just want to review a little bit. You might remember back, I know in Calc 1 we did this. If you had a graph, if you knew what y equals f of x looked like, all right? You knew what the graph of that looked like, and you had instead f of x plus 2, what happened to the graph? It got raised 2 units. If you had y equals f of x minus 2, what did happen to that? You lowered it. Remember that? 2 units. What happened when you had it inside? Remember, it was just the opposite? Instead of, since that's, notice plus 2 raises it up to minus 2 lowered. When you had a minus inside the parentheses, you moved to the right 2 units. And the reason is if you figured out for this new function f of 2 for the new function is doing what f of 0 did for the other function, so you're moving it 2 units. And if you had this, that moved it to the left 2. And lastly, what if I did this? Whatever was positive became negative, whatever negative became positive. You reflected it through the x-axis. Well, we can do the exact same thinking if we're in a three-dimensional space. What if you knew, now see, describe how the graph of g is obtained from the graph of f. So you know what f looks like, and g is f of xy plus 2. Remember, this is your z coordinate. So if we're adding 2 to our z coordinate, what are we doing? We're raising it 2 units. Now this one I didn't go over, but what if you multiply 3 times all yours? What are you doing? You're multiplying each z coordinate by 3. Okay, in other words, you're stretching it. What if you have this? G of xy equals the opposite of f of xy. Your z coordinate is positive, it now becomes negative. It was negative, it becomes positive. You're reflecting it through the xy plane. Now, what's this one going to do? What if you, instead of x, we put x minus 2. Wherever we see x, we put in x minus 2. We're going to shift it 2 units in the positive x direction. Just like f of x minus 2 shifted you to the right 2. To the right is positive x direction. You're going to shift to the positive right 2. And lastly, this one's going to shift towards, it's going to shift 3 units towards the minus x direction. And after you shift it 3 units in the minus x direction, then what's the minus 2 going to do? You're going to shift it 2 units in the positive direction. Okay, well, I think we covered plenty for today. So let me give you what your assignment is. First of all, look over pages 923 to 933. They cover just exactly what we covered in the lecture today. And then on pages 933 to 936, we need to do numbers 1, 5 through 29, the odds, 37 to 43, the odds, 59, 61, and 63. Okay, and have fun studying, and I'll see you next time. Bye-bye.